In coastal areas where rivers meet the oceans, it has been necessary to connect land points with bridges to facilitate transportation in these locales. There is such a place in the San Francisco Bay Area called the Carquinez Strait. The Carquinez Strait is located where the Sacramento River and the Napa River flow into the San Francisco Bay Area. It also separates the San Pablo Bay and the Sassoon Bay. The roadway is Interstate 80, one of our national highways that terminates at Highway 101 in San Francisco after crossing the United States from just 4 miles east of New York City. The two bridges at this site carry the traffic in opposite directions. Drivers pay a toll at the northbound location. The tolls go toward offsetting the cost of operation and maintenance of the bridges. The first bridge over the Carquinez Strait was completed in 1927. It was privately financed and operated until 1940, when it was taken over by the state of California. The second Carquinez Bridge was completed in 1958. It was designed by the California Division of Highways. It was very similar in design to the 1927 bridge, but it incorporated many advancements, including the use of welded high-strength steel. Each of these bridges is a cantilever design. A cantilever is like a bracket, jutting out into space, attached to an abutment which anchors it to the ground and supported by piers, usually in the water at both ends. Then a suspended span is placed between the two overhangs. The cantilever design allows for building each end of the bridge without disruption of the navigation below, and enables the builders to place the piers closer to the shoreline and in shallower water. The Loma Prieta and Northridge earthquakes in California brought to the forefront the incredibly destructive possibilities existing in nature. It was then decided by officials of the California Department of Transportation that a complete review of our state bridges was in order. From that time, a massive project was undertaken to inspect and retrofit all of the toll bridges in California. The two bridges over the Carquinez Strait were included in this program. While the 1958 bridge was a candidate for retrofit, it was concluded that the 1927 bridge was not strong enough. It was decided to replace the bridge because it would cost more money to fix it than to replace it with a new one. In addition, a new bridge would enable the engineers to increase the traffic lanes to accommodate the ever-increasing traffic on Interstate 80. 4 types of bridges were considered for the replacement of the old 1927 bridge. The one finally selected is a cable suspension bridge. This design was chosen based on superior seismic performance, a shorter construction schedule, less risk of impact due to having fewer piers in the water, less maintenance, better aesthetics, and less construction risks. The functions of the parts of a suspension bridge are simple to understand. The pilings attach the towers to the ground. The towers hold the cable up. The anchorages pull the cable outwards and downwards. The hangers connect the deck to the main cable. The function of the deck is to carry the traffic. Getting all of these parts to act in harmony is the function of the designer and the construction engineer. 2 forces that act upon a bridge are compression and tension. Compression is a force that acts to compress or shorten the thing it is acting upon. Buckling is what happens when an object is unable to overcome compression. Tension is a force that acts to expand or lengthen the thing it is acting upon. Snapping occurs when an object is unable to overcome tension. One job of the engineer is to make sure that every part of the structure and the foundations and the ground can sustain the forces they are subject to. In poor ground, a deep foundation is needed to take the forces to the point where the ground can take over. In water, the same scenario. The deck must possess enough local rigidity to prevent flexure as vehicles pass. The hangars must help maintain this rigidity to prevent undesirable vibration caused by wind, traffic, and seismic events. The construction of the new Carquinez Bridge is truly an historical event. It is the first suspension bridge in the United States with an aerodynamic steel deck. It is the first suspension bridge in the United States with concrete towers, and it is the first suspension bridge with concrete towers in a high seismic zone. It will be the first suspension bridge built in the United States since 1973. When completed, the bridge will extend 1,059 meters from the end of the north abutment to the end of the south abutment. The towers will rise 131 meters above the water. The distance between each of the main towers will be 728 meters. With a transportation project like the new Carquinez Bridge, a structure that carries thousands of vehicles every day, it is important that the California Department of Transportation be assured that every component of the bridge meets the highest standards. In the Structural Materials Testing Lab in Sacramento, the California Department of Transportation performs quality assurance testing on many of the structural components of the bridge.
For the Carquinez Bridge, we tested fasteners, various types of fasteners, rebar products with ultimate splices. The main cable was tested for the suspension cable. The tests that we do here are tensile testing of several different products. We do tensile testing of pre-stressing strand and post-tensioning components. Quality control is the responsibility of the manufacturer or vendor to assure that their products are quality products that conform to the specifications required for that product. Quality assurance is done by the purchaser, in our case Caltrans, to make sure that those products conform to those specifications and meet the need of Caltrans.
The piles are what attaches the structure to the ground and provides stability. Each of the two main columns is supported by 12 piles, 3 meters in diameter and 90 meters in length. Concrete pile caps are used to transfer vertical and lateral loads between the piles and the towers. A reinforced concrete footing was fabricated off-site and then floated to the site, lowered into place by the falling tide, and secured to the piles. The design challenges for the two anchorages were much different. The south cable anchorage transfers the thrust of the cables via massive concrete anchor blocks and batter piles and vertical piles. The batter piles were steel shells driven through soil and bedrock, then filled with concrete. There were 380 piles. Then the anchor block was constructed over the piles. The splay chamber, where the cable strands are connected to the anchorage, rises above the ground 18 meters. The north anchorage was excavated 20 meters into the bedrock of the bluffs rising above the north side of the strait. The rock also serves as a bridge abutment. The concrete anchor blocks and the splay chambers are benched into the rock beneath the roadway, and only the relatively small saddle housings extend above the ground. The towers are reinforced concrete portal frames. The slightly inclined columns allow for clearance for the width of the continuous steel deck, while allowing the main cables and the suspender cables to hang straight to support the deck. The bridge has 3 towers, the 2 main towers that support the roadway, and a third, called the transition tower, that connects the suspension portion of the bridge to the new south interchange. At the top of each tower on each side is a device called the saddle. This is the location where the cable rests on top of the tower. Extensive preparations had to be made before the main cables could be constructed. First, a footbridge had to be constructed from each anchorage to the tower tops across the strait. The shipping channels had to be closed for a period of hours for several days so that the steel cables could be pulled across the strait and lifted into place by cranes and winches. The purpose of the cables was the construction of a footbridge, which would allow workers a working platform in preparation for spinning the cables. The spinning of the main cables was one of the most fascinating techniques in the construction of the bridge. The operation, known as aerial spinning, was developed by a man named John Roebling over a century and a half ago, and it has changed little in all of these years. The term spinning comes from watching the multi-spoked wheels rotating as they carry the wire back and forth over the towers and between the anchorages. The intent is to place parallel wires at equal stress and then bind them tightly together in a unified cable of integrated strength and stiffness. Workers stationed along the footbridge guided the wires into the saddles and the cable formers and secured it to the anchorages at both ends of the bridge. The aerial tramway was equipped with spinning wheels that pull the wire from reels located at the north end of the bridge through a counterweight tower that maintained tension on the wire as it traversed the towers and looped through the anchorage. The wheel then repeated its trip back and forth until each main cable was composed of 37 strands consisting of 232 individual wires, for a total of 8,584 wires in each cable. The technique employed to maintain the correct tension in the wire was called the controlled tension method. In this method, the wires pass through the counterweights that are calibrated. The counterweight's position and movement are monitored and controlled by a computerized system that maintains the tension at a constant. Adjustment of the cable strands was performed in stable temperatures and when the bridge tower's movement was at a minimum. Once all the strands had been placed, the cable was compacted and large steel casings called cable bands were installed. The cable bands hold the vertical wire rope suspenders. The lower end of the rope suspenders attach to the deck. This configuration enables the cables to carry the load of the deck and the traffic. While the tower and cable construction were being completed, the fabrication of the deck sections were occurring in Nagoya, Japan, at a company called IHI, a well-known engineering, fabrication, and construction contractor. The deck was designed to carry 4 lanes of traffic, 2 shield lanes, and a bike and pedestrian lane. The deck is an orthotropic box girder. A girder is a horizontal structure member supporting vertical loads by resisting bending. Orthotropic means being able to resist stress in multiple directions at once. Unlike the truss systems that were employed in the design of the Golden Gate Bridge and the west side of the San Francisco-Oakland Bay Bridge, the Carquinez Bridge is composed of thin plates joined by extensive welding into a highly efficient, completely enclosed girder. However, the roadway was fabricated in sections and shipped to the construction site from Japan. A typical section is 50 meters long and 29 meters wide. Each of the ships carrying the girder sections was anchored under the bridge, and the sections were lifted into place. Strand jacks, or winches, were used to raise the girder sections into place. A strand jack wedges steel suspender strands and pulls them through the device, thus lifting the load bore by the suspender strands. One set of wedges grips the strands while the other set is extended. Then the load is transferred to the extended wedges as they contract, pulling the strand through the body of the jack. It took an average of 4 hours to lift one section into place and to transfer the load from the jacks to the permanent suspender cables. After the deck sections were in place and attached to the suspender cables, they were bolted and welded together to form one continuous girder the entire length of the bridge. Drastic alterations had to be made in the landscape on both ends of the bridge to make connections to the new bridge and to continue to allow traffic flow on the old bridge. In addition, careful plans were made to incorporate modifications and to design structures that would blend in with the environment in a way that would entice the local residents to welcome the improvements. On the north end of the bridge, an abutment was constructed which would attach the roadway to the ground.
One of the reasons for selecting a suspension bridge is clearly visible from here on top of the South Tower. You notice the existing two bridges have a large pier in the middle of the channel. And the suspension bridge allowed us to clear nearly the entire strait without doing any marine work in the middle of that channel and impacting ship traffic during our construction. And also at some time in the future, when these bridges reach the end of their service life, they can also be replaced with a suspension bridge, allowing us to clear the entire channel of this obstruction to shipping traffic. In addition, over the past couple of decades, there's been an upsurge in construction of suspension bridges. There's been a lot of new techniques, and there's a lot of material and manpower and know-how available on the world market. And we thought this would be a very good time to potentially get a good competitive bid on a suspension bridge. And that's indeed what happened. We got a very experienced contractor with a lot of equipment left from previous jobs and a very good competitive bid.
The construction of the new Carquinez Bridge is a testament to hard work and dedication of the iron workers and concrete workers who worked in dangerous and difficult conditions on this project. Thus, it is only fitting that the bridge will carry the name of a bridge-building legend, Alfred Zampa. Mr. Zampa gained his reputation from working on the 1927 and the 1958 Carquinez bridges, the Benicia Bridge, the Richmond-San Rafael Bridge, the Bay Bridge, and the Golden Gate Bridge. Al Zampa was present at the groundbreaking ceremonies for the new Carquinez Bridge at the age of 95, but he died several months later before the bridge was completed. Alfred Zampa Memorial Bridge reaches up from the ground below to span the Carquinez Strait as a functional sculpture that pays tribute to man's ability to provide form, beauty, and function for the purpose of meeting the transportation needs of the people of Northern California.
And the suspension bridge allowed us to clear nearly the entire strait without doing any marine work in the middle of that channel and impacting ship traffic during our construction. And also at some time in the future, when these bridges reach the end of their service life, they can also be replaced with a suspension bridge, allowing us to clear the entire channel of this obstruction to shipping traffic. In addition, over the past couple of decades, there's been an upsurge in construction of suspension bridges. There's been a lot of new techniques, and there's a lot of material and manpower and know-how available on the world market. And we thought this would be a very good time to potentially get a good competitive bid on a suspension bridge. And that's indeed what happened. We got a very experienced contractor with a lot of equipment left from previous jobs and a very good competitive bid.